right, our next talk is going to be error handling and MPI continuations by Joseph Schuchart.
I'm Joseph. Most of you probably know me by now. This was a short paper that we submitted because we really think it fits well into the scope of EuroMPI. It was work with Aurelien and George, trying to integrate proper error handling into MPI continuations. Just to let me start giving an overview over MPI continuations. So as you all know, MPI provides all sorts of nice non-blocking things like two-sided collective communication, RMA, and IO. Typically, we get a request that represents that operation. We can test and wait for that request. And with continuations, what we add is that we can register a callback for that request, and we will get a notification once that callback is complete. What this incidentally does is it basically moves the request handling back into MPI. So we don't want to handle those requests. We don't care about those requests. All that we care about is that that operation eventually finishes and we get a ping back that it's complete now. So we add some form of events. The canonical motivating example that I have is OpenMP tasks, and that was mentioned a minute ago in the previous talk. This is what you intuitively would do, and if you have ever tried to do that, you realize that it doesn't work because OpenMP task here doesn't do what you think it might do. There's a good chance that you will deadlock here because it doesn't yield necessarily. So what you would do with continuations is you would post that receive, you get a request for that receive here, and then you call MPI continue, give it that operation request. So far, you would just return the request to MPI. You're done with that request, you don't care about it anymore. You pass a pointer to a function that will be called once the operation is complete. Is this complete callback here? You pass it the event because it's a detached task. OpenMP will give you an event, and I'll show you what the completion callback actually does. And then you pass it a continuation request, which I will come back in a minute. The completion callback actually just calls OMP fulfill event, and what that does is release this dependency here on the variable val, and once that dependency is released, this task here that consumes that value can execute. So now we are able to completely hide the latency for the communication. We don't have to execute a task waiting for our communication to complete. Once it's complete, we get a callback and we can execute the next task. What has changed since, if you've heard me talk about this previously, what has changed since previous iterations of this proposal is that we passed an MPI status into the callback. We don't do that anymore because it doesn't work as we would like it to work. Instead, we pass an error code, and the callback now has an error code itself. So you could actually mark a continuation as being failed. And I will come back to that at the end of the talk. Continuation requests are still there. I haven't shown how to initialize them. What they are is there's special kind of requests in MPI that you use to accumulate continuations. So think of it as a bucket. You throw all the continuations into that continuation request, and eventually you can test or wait for them to complete. So if you have 100 continuations, you have to only test for one request, and we'll tell you if all your continuations are complete. As a side effect, you also progress the execution of continuations because we don't typically have progress threads in MPI. So someone has to yield us some CPU cycles, and we do that by testing or waiting for the continuation request to complete. You initialize a continuation request with MPI continue init. In the current state of the proposal, it has two parameters here that control the maximum number of continuations that are executed when you poll on the continuation request using MPI test, and a bunch of flags that you can specify. For example, that continuation should only be executed when you're polling on that request. And then you get a continuation request back. And then what you can do is here we have a loop, we iterate, we post a bunch of receives. And for each receive, we want to have a separate callback. So we call MPI continue on each of them. And in the end, we just wait for all operations to complete and all callbacks to have occurred. And once all of that has happened, MPI wait will return because everything is done. So that's the idea of continuation request. And this is the current API overview. We have, in addition to MPI continue, we also have MPI continue all, which basically you can give it an array of requests, and it will the continuation will be executed once all of those requests are complete. So you can wait for, or you can have a continuation on several requests. I will only focus on MPI continue in this talk, but the same applies to continue all. What's important here is that this is as far as my UML skills are going. So you have a continuation request. You can register multiple continuations with the continuation request, as we've seen before. And you can have multiple MPI operations for one continuation. You can't have multiple continuations for one MPI operation. So there's always one callback per operation. So to the title of this talk, what do we do if an error occurs with our continuations, right? Somewhere in our big MPI library, we detect that there was an error. What do we do with our callbacks? How do we handle our requests? What are errors in MPI anyway? I'm sure everyone always checks the return code of the MPI functions, but no one ever sets a proper error handler, so nothing will ever happen there. In MPI, we can detect faults in many places, for example, in the network. So any lower level communication library will tell us that the network went down or that we lost a connection to a peer, or we can have some errors in the application software too. If they typically by default lead to the immediate abort of your application, but it can also you can also return in case of an error. You do that by setting an error handler here, MPI errors return. In that case, you would get down here, MPI test all would return some error value, and you can handle that error if you can do that. There are two types of, there's completed requests, of course. If the operation is completed, there are failed requests, which are returned to MPI, and you will get some status in your MPI status object, which are then propagated back to the application, and you can analyze that. And there are pending requests that are returned to the user where we don't really know the status of them. They're kind of zombies. We have identified two types of errors. The first one is pretty clear, and that's basically the only error you would get in current MPI, which is in-band errors if the MPI implementation detects a communication error. So think about this channel here going down, so we lose connection to our peer. Then we know that this operation has failed. We can mark the request as failed, and as soon as MPI wait tries to wait for that request, it will check the status of the request and see that the request is failed, and it will either abort or return. So those errors are directly tied to an operation. With ULFM, we actually get another class of errors, which is quite interesting. So as you probably know, Aurelien is working on ULFM, so we also incorporated ULFM into this work. In ULFM, we get more fine-grained fault recovery, some sort of resource management in the event of a fault, which involves that we can revoke and shrink communicators. So this gives us out-of-band errors. Now, For example, here, some of our peers could have revoked the communicator, which means that communicator is invalid, and we all the operations that are still active on the communicator and have not completed yet will fail. So in MPI await, again, we look at our requests and we see that the communicator has been revoked, and then we cancel the operation because we have no guarantees that will complete, and return an error from MPI await. But the important part is here that we don't get the error from the operation, we get the error from some higher level, and we have to go down into the request and check whether the request is dependent on that revoked communicator. Pending requests in MPI, there is an error code called MPI error pending. It's kind of a Schrodinger's request, where we get it back from MPI, and we don't know what its state is. It could be complete, or it could be pending, or it could be incomplete. We have to test, wait, or cancel to get it into a definite state. So we have to go back to MPI and check. The important part here is that we have to do something with those requests. So we need those requests. And it's up to the application to figure out what to do next. ULFM has its own pending request state. If you do a receive of MPI source any, and one of your potential senders fails, then ULFM will mark the request as MPI POC failed pending, and give you back the request, and you can decide what to do with it. The important part here is that at that point, we don't know if there will be a sender that will satisfy this request, so we have to mark it in a special way. And again, it's up to the application to figure out what to do next. Because the request might be satisfied by someone else, not by the failed process. Why is this relevant for continuations? Well, we have to return from that MPI await on our continuation request eventually. Otherwise, we will deadlock, right? We will just sit there waiting for all our continuations to be executed, which they will never do because the communication operations will not complete. We have to set proper statuses. When you register a continuation, you can pass an array of statuses for each operation that you attach the continuation to, and we kind of have to somehow have to fill those statuses. And if there is an error, we want to return the incomplete request back to the user, because the user has to do something with them, has to either attach new continuation or decide that he wants to cancel those operations because the user knows that they will never be satisfied. Plus, we have to handle those pesky out-of-band errors that ULFM hands us now. What we should not have to do in MPI is allocate unbounded buffers. We don't do that in MPI. We don't want to do that because it's a potential trap. So we don't want to create copies of our request buffers. For example, the user could hand us a million requests, and we don't want to copy them around. So all the request buffers and the status buffers have to be allocated or managed by the user application. So the overall, the high level view on how we think we want to handle errors in continuations here is the important part is that we cannot test those requests directly. So once you have given us the request, you are not allowed to test or wait on those individual operation requests. The only access path to information for those requests is the continuation request, which you can wait on or test on. So if an error happens, you will come out of that wait with a return value that is not MPI success. And at that point, you can gain back access to those requests. And I will show you in a minute how to do that. The important part is that if an error occurs, we will interrupt the wait on the continuation request. So the question is now, how do we detect that a continuation request has failed? and how do we give you back access to those failed requests. With in-band errors, it's fairly straightforward. Again, if this link here goes down, we mark the operation as failed. We can walk up to the request because usually we have a link from the operation to the request. The request has a pointer to the continuation because it's a one-to-n relationship. It's easy. We just need to add a pointer to the continuation object. And the continuation has a pointer to the continuation request because, again, it's a one-to-n relationship. And then once we call MPI wait on the continuation request, we will see that the continuation request has been marked as failed, and we can return from MPI wait because we see that it has failed. With out-of-band errors, it's not so straightforward because now the only thing we have is the continuation request. None of the operation has failed yet because it's only the communicator that has been revoked. So now we have to traverse down from the continuation request. We have to check all the continuations. We have to look at all the requests if they are affected by this revoke. And if they are, then we can walk back up and mark the continuation as failed and eventually mark the continuation request as failed and come out of MPI wait with an error. The point here is that we need those the operation requests. We need access to the operation requests in order to handle the error that stems from revoking a communicator. As a consequence, we now require that the request buffer is persistent until the continuation has completed. This is a change in the API that is quite significant. I was very hesitant to do that for many weeks until I was convinced that this actually matches what we do with other non-blocking operations in MPI. Think of a continuation as a non-blocking operation. If you have non-blocking collective operation, alt-LV, for example, all the buffers you put into i-alt-LV have to be persistent until the operation is completed. And the same is not true for continuations. The request buffer and the status buffer have to be accessible until the continuation has been executed. And before we call your request, we will set the request. Before we call your continuation callback, we will set the request to MPI request now. I'm sorry. Right. So now we have to hide this, put the request in our structure that we allocated so that it's valid until the callback is invoked. We cannot put it on the stack anymore. Now, that is me. I'm a user, and I say, I really don't care about errors. Please don't make me allocate extra memory because it's expensive and it's really not worth it. And then the other me would say, but you really should care about errors because that's what we do this all for, right? And then I will say, but MPI errors are fatal. I really don't care about errors. If there is an error, everything will fall apart, and I don't even want to have access to that request anymore because my application will terminate immediately. And then in that case, okay, so you can pass MPI Correct volatile to MPI continue. We will honor that. We will respect that the request buffer is not accessible after the call to MPI continue has returned. But if there is an error, we cannot do anything for you anymore. If there is an error that and the application does not and MPI doesn't call the MPI errors a fatal error handler, then it's basically undefined behavior. But what you can do now is you can go back and have your request on the stack. If you don't change the error handler from the default error handler, you can pass that flag here to MPI continue, and you will never get here, or you should never get here really, because that is undefined behavior now. But you can save an allocation if you want to do that. The second question is, how do we return failed continuations back to the user? So we detect an error, we tell you that there was an error on your continuation request and your error handler is not errors are fatal, but errors return. For that, we have added a new MPI function, MPI continue get failed, which you pass the continuation request and you pass a count pointer and an array pointer, a pointer to a void array. We will continuously give you the callback data that you passed us to MPI continue for all the failed continuations that have not been executed yet. And that way you regain access here to your messages that you have previously given us in MPI continue. And then you can check the status and you can cancel the request, for example, if you get MPI proc fail pending. So you get full access to the request and the status if they were behind that pointer. And you do that as long as the count will be updated to the number of actual elements that we put in this request here. And as long as the count that you put in is the same as the count that you get out, there's a good chance that there are more failed continuations that we will give you. Once it's not the same, once we return 0 or 8 or something smaller than what you passed in, this is the last batch of failed continuations that we will return. And from that moment on, you can start adding new continuations. Now, this is the other way, the other aspect that I was quite hesitant in the beginning. There might be a good case where you say, well, but I know how to handle my errors inside my callback. I don't want to do this outside of the callbacks because I just need to mark my process as failed and I will never contact it again. I don't have to shrink my communicator or whatever. Just call my callback even though it has failed. And then you can pass MPI cont invoke failed, and we will invoke the completion callback even though there was a failed operation. We will give you an error code here. So normally, if you don't specify this flag, this will always be MPI success. If you specify that flag, you should check that this is actually MPI success. And if it's not, you have to handle the failed operation here. And then you should always return MPI success unless you want to mark the continuation as failed, then you can return any MPI error code. If you return an MPI error code here, it will be basically propagated outside of the MPI wait, and you can also handle the error again here. So this is our way to propagate failures out of the continuation callback back out of MPI wait. To review the changes to the API that we've made during the process of adding error handling to continuations, the callback itself now takes an error code and returns an error code. So that way we can pass errors into the callback and propagate errors out of the callback and out of MPI wait back into the user code. And you can ask us to invoke a failed continuation. The request buffer must be persistent until the completion of the continuation callback, except if you really don't want to do that and you know that you're always using MPI errors are fatal. In that case, you can specify MPI contract volatile, and we will not touch the request after MPI continue has returned. And we have added MPI continue get failed so that you can actually ask for failed continuations and you will get the callback data back, which hopefully contains all the important information that you need to handle that failure. We have done some preliminary overhead measurements here. This is in our OpenMPI reference implementation. So as you can see, just using continuations instead of doing I receive and send, and the wait adds a little bit of overhead. So about 0.03 microseconds. If we enable multi-threading, the overhead is a little more because we have to do a little more atomic operations, unfortunately. Still, overall, the overhead is rather small compared to like the feature that you get for it. And if you enable the error handling, so here we actually passed the rec buff volatile, I forgot what it was, the volatile request buffer flag, then you see that there's almost no additional overhead here. So adding the error handling in the end wasn't that expensive, not as expensive as I expected it to be. So let me skip that. Okay, so to end my talk here, error handling is part of MPI. It will potentially be extended by ULFM. We realized that it requires some careful reasoning about the control flow and how we can propagate errors back out of that asynchronous operation into the user code. It does add some complexity, especially for the implementations, to handle basically rare cases, right? Handling errors is a rare case. You don't hope ever to have to do that. Some people do, but it's a 1 in a million thing. But it impacts the design of anything that is being added to MPI that deals with non-blocking operations, and you have to think about it carefully. I plan to update the proposal text for the December meeting, and I hope to be able to read it there. We'll have to see if there's time. And of course, I want to use more. I want to find more use cases. So if you have a use case for this, please let me know in the break. I'll be happy to work together. We already have a few, but it's always good to hear from potential users and see what they need, and see if the API that we have right now matches their needs. So with that, I'm right on time. The project or the proposal text is hosted in the hybrid working group. And if you have any questions, feel free to shoot me an email or catch me in the break. Thank you.
Great. Any questions?
Oh, let's see. No. I know error handling is super dry. It's it puts everyone to sleep.
It sounds great to me. So at the risk of asking a question that's kind of, Rolf has a question. All right.
Oh.
Go ahead, Rolf.
Only a short question, a small detail. In all your code examples, you directly test with error codes returned. Do I understand correctly that in the real application, you must translate the error code first to error classes, and then you can test with these error classes you have provided in your if statements?
I have no idea. This is beyond me.
Okay, then.
Not necessarily, but maybe.
Maybe. Okay, good. Thank you.
So you mentioned how to handle things like errors are fatal, which is relatively simple, how to handle the plethora of issues that come from ULFM. I wonder if you have discussed or talked about any impact that might come from other fault tolerance proposals like the reinit proposal or things like that. Reinit may be more on the errors are fatal side. Is that what you were thinking?
That's actually a good question. So my expectation is that in that case, everything just goes away and we start anew, right? So all the complexity that we have here is not really needed. I don't know, you probably could tell me more about what happens in reinit, but yeah, I mean, everything is started from the beginning, right? So
yeah, I think that's probably what I would expect, but I didn't know if you had any other thoughts.
It would be easier for us, but I mean, even without ULFM, there are error handles in MPI that we have to handle already, right? So we had to do this work anyway, even if ULFM doesn't make it into the standard.
All right, let's thank Joseph one more time.
Yeah. Sorry.
Just one quick question. In the MPI continue overhead, is it just the function call overhead?
It's everything. It's the function call to register the continuation. It's the callback invocation at the end. So we have to set up more data structures, and because with the error handling, we need to put some things in shared data structures, which sucks, but yeah, that costs a little bit. But it's only a few hundred instructions in the end.
Okay, thank you.
Thank you.